Bismillahirrahmanirrahim. Greetings. Every curve consists of infinitely many line segments of infinitesimal length connected to one another side by side, each of them having a slightly different slope. Notice that I have used the word slope here, I haven't defined it yet. Now, that means that the backbone of every curve is a straight line. And that also indicates that straight lines are very important in mathematics. Now, we all know what a straight line is and what a slope means subjectively. Now, in this video lecture, we are going to discuss them, we are going to investigate about them objectively with the intention of coming up with an analytical representation of line or analytical equation of a line that will free us from our dependency on geometry, on drawing. So, let's start, shall we? Now, I have, by the way, drawn this one for you if you want. I think it's large enough, I don't have to zoom it out for you. And that is a line that I just mentioned, infinitely many line segments of infinitesimal length, and each of them having a slightly different slope, and every curve consists of them. Now, let's, in our investigation, don't forget what our goal is, to find analytical representation of a line. Now, from plane geometry, we know that every line consists of two distinct points determines a unique line. And that is a postulate in plane geometry that is also known as Euclidean geometry, and also is true in coordinate geometry. But in other geometries that we are not going to talk about to discuss that one, the two distinct points may not determine what as a unique line, but possibly many lines can pass through 2 points. But that is a different geometry. Now we are going to draw a line, let's say two distinct points. Let me select the points to be just these 2 points. And this line, these 2 points determines a unique line. Now this is the line I draw. Now this line is unique. And what that means impossible in plane geometry. Impossible, you can draw another line different than this line that can pass through these 2 points. Again, that is one of the postulates in plane geometry, and postulate is something that we take it for granted as a building block, and we start from that, and we cannot prove it, because we will reach a point that we have to start from that point, and that is what the axioms and postulates are. Now, stand back and stand by and look at the line that I draw, and see what kind of property we can find in this line so that we can extract those properties, make a list of them, and see how we can use them in our advantage. Don't forget what our goal is, to find an analytical representation of a line. So when you look at this line, what do you notice? We notice that every right triangle that we draw, such that the hypotenuse of that is on this line, those right triangles are going to be similar. Hopefully we know what the meaning of similarity of triangle means. Now I have the drawing, and let me put it up if I may, and see what I mean by that. Now here, this is our line, and every right triangle, as you notice, if I draw in that, they are similar in a sense that, look at that, the corresponding angles, this angle is congruent to this angle is congruent to this angle, all of them have 90 degrees, and this angle is congruent to that. The proof of that is very elementary. It's a junior high, and I'm not going to go through that. So we know that the corresponding angles of these triangles, no matter how small or how large they are congruent. Therefore, the corresponding sides of these triangles are going to be what? In corresponding sides are going to be in ratio proportion. And then it looks like in reality is that one of the triangles, no matter how small or large you get it, is that if you zoom it out, you get a larger one, or if you have a larger one, you can zoom it in. So all these triangles are zoomed in and out of one single triangle. You can look at it in infinitesimal world as very, very small, or as a very, very large triangle. No matter what, all of them, they have the same property, which is what? Which is the ratio of that they are similar. That is one observation we make for looking at this line. What other observation do you make? Don't forget, you are stand back, stand by, looking at that and trying to extract information so that we can use them for our benefit. Now, we notice also that any other line, let me just maybe draw one, that is parallel to this line. Let's just let me draw that one line parallel to that, let's say. Now, any other line parallel to our line, any right triangle that we draw on this line, any right triangle that we draw on this line, no matter again how small or how large it is, this triangle is also similar to any other triangle in this line. Don't forget, this line is parallel to that. So any other triangle, right triangle that we draw on this line is going to be similar to this one. That's another thing we notice. What else do you notice? We notice that all these lines, they make the same, that they are parallel, they make the same angle with what? With the horizontal axis, horizontal line. So if you draw any horizontal line, the line or line will make an angle alpha with that line, with the horizontal line. That means that we can also discuss the matter of analytical approach for the line from the point of angle. And with angle goes trigonometry. So looks like we may also bring the science of trigonometry in our advantage and see what kind of analytical equation we can get out of it. Now that we know the ratio of this to this is same for all triangles in that line, we call it rise over run. We know that, so let's use one of them as a typical. Use that triangle as a typical triangle, and let's call this one y2 minus y2 x2 comma y2, this point, and this point let's call it x1 comma y1. Then this length will be y2 minus y1. Is that right? y2 minus y1. will be the side, the length of this side, and the length of this side will be x2 minus x1. So let's use this triangle as a typical triangle, and since this y2 minus y1 over x2 minus x1 remains same for all other triangles, looks like we have reached one of our goal. And based on what we notice, we can make definition for a slope of a line. So this will be an analytical definition of a slope of a line. Y2 minus y1 over x2 minus x1, which is a ratio of two numbers, therefore a slope is a real number. Now from now on, the word slope will be an analytical term for us. Isn't that fascinating? From this observation, we came up with fascinating what? Definition of a slope. Now, I have written that one. Let me also put it on the bulletin board. This is my bulletin board. Now, I'm just repeating what I just said a minute ago, and that is this side is y2 minus y1, this side is x2 minus x1, and this remains same for all other points in the line, for all other triangles, right triangles and this, that we can construct on this line. Therefore, we use y2 minus y1, which is the length of this, over x2 minus x1, which is the length of this, and we call this one a slope of this line. So we came up with a nice looking definition, analytical definition for a slope. Okay, now let me go to see how we can come to a possible equation of the line from, again, our observation from what? From the line. So don't forget what we did. We draw a straight line, and then we stand by, and look at it and contemplate, think and reflect, and see what kind of information we could get from that line that we draw, and so that we could use it for our advantage. Now the lines that I'm drawing, they are not in a scale, but I'm using them as a kind of visual aid to assist me to come to my goal. So again, I'm not drawing them in a scale, so I'm not using I'm using a coordinate system, but I'm not drawing my lines in a scale. Okay, now this will be my typical triangle, I said, in that. Now, let's see, if I select any points in the plane, randomly select, let's say this point. If I select any point in the plane and connect that to this point, and make a right triangle out of it. Let me do it. And make a right triangle from this point to this. I don't even have to continue. As you notice, the slope of this one will be different. I shouldn't say a slope because I say it's an analytical term. So let's say a steepness or a slant of this line is already different than this, so I don't have to continue further, but I do it anyhow, and I try to form a right triangle out of this. Okay, this is the right triangle that I'm forming, and look at this triangle that I just formed is what is not going to be similar to this triangle. 100%, you can see that seeing is believing, So I select a point on here, didn't work. Now if I select any other point in the plane, and I connect it and make triangle out of it, right triangle of them, some works, some doesn't work. Alright? So that is another observation that I'm making. And that means what? That means that certain points in the plane will satisfy the typical triangle that I draw, I talked about the ratio of rise over run in a sense. Certain points will satisfy, but many other points they do not. So what are those points that satisfy this ratio? The ratio of this side over this side was what our definition of what? Our definition of a slope. And look what happens. If I select a point here, and then we will see if we construct a right triangle, that right triangle will be similar to this. And this point, and this point, and this point, there's infinitely many points in fact, but those points are the points that if we connect them all together, they form our line. Let's call that line L. We'll make our line. So those and only those points, such that, let's call it XY, at that point, such that Y, the Y coordinate of that point, minus the Y coordinate of one of the 2 points of this, doesn't matter which one you take. Let's say we take x1, y1. Then y minus y1 over x minus x1 will be the slope, that will be what? Will be the same as ratio of this length to this length, which is a typical triangle we selected. So y minus y1 over x minus x1 is same as y2 minus y1, which is the length of this, over x2 minus x1, which is length of this, which is the slope of the line. Fantastic. Looks like we have also succeeded to come up with the equation of the line. Now let me put it. Now let me put that one in set notation, because we did talk the set of all points such that y minus y1 over x minus x1 is same as y2 minus y1 over x2 minus x1. So let's talk about the set notation, set raster notation point of view. So if we do that, I have put that in writing, and I think they are hopefully large enough that I don't have to zoom in and out for you. Now look at this one. The set of all x and y in the plane such that, with the condition that the y coordinate of that point, minus the y coordinate of one of the 2 points of our typical triangle that we draw, over the x coordinate of that point minus the x coordinate of our point on the line, either x1, y1 or x2, y2, doesn't make any difference. That will be the same as what? Will be the same as a slope of the line. We already defined what the slope means, which is y2 minus y1 over x2 minus x1. Now, it is kind of a standard, almost every textbook I have seen, they use the letter of M, standing for a slope. So let's be consistent with that. And then instead of writing y2 minus y1 over x2 minus x1 each time, we use the letter M. So the letter M stands for the slope, and our typical triangle, the first one, did give us what the slope of our line was. Now, I like this notation of a line much better, and I insist to use my students to use this one as an equation of the line, because there is more, kind of give you more in-depth knowledge about that. You know that you are using what? You are using the similarity of triangle, and also the slope text form in your mind, the picture of that. Now, there is other way we can do it, which is we can also multiply both sides by x minus 1 in this case, or cross product, and then we come up with another formula that we can call it, maybe I have written, in fact, we can call it the point slope form of a line. So let me also put that one on the bulletin board that I have, and see what it can come up with. So this one I have already explained. We know that is M, so y minus y1 over x minus x1 equals to M. Now, very elementary algebraic manipulation, I multiply both sides, these two sides together, and I come back with this formula, which is exactly the same as this, they are equivalent. But as I said, I put this one in the box because I like this form of the line to present it better. Okay, now this is called a slope, point a slope of a line. Point a slope of a line. Which means if I have a point on the line and we know the slope of the line, we can write the equation of the line. Now, one advantage of this to this is that we can also look at this from the point of function relation. So this is also a function about that y will be an independent variable and x will be a dependent variable. So we are dealing with function and we can sketch the line that way. But again, I insist to use this one because to me is this notation for representing line is a better one. Okay, now what else do you notice? Let's just don't forget what we were doing. Stand back, stand by, concentrate, contemplate, think and reflect and see what we can come up with. We notice that every line, except vertical line, will hit, will intersect the y-axis at some point, 100%. I don't even have to call it axiom. Is a fact. Let's call it axiom even. So every line except vertical line, what I come to vertical line, except vertical line will hit the y-axis at some point. So why not to take our point to be the point that the line intersects with the y-axis rather than x1, y1, and see that we can come up with equation of a line an easier way in a sense, and that is, I have drawn this one, let me show it. So our line L, instead of taking x1, y1 or x2, y2, one of the points in the line, we select our point to be what? The intersection. And this point, the coordinate of this point, x is 0 and y is some y1. But most of the textbook, they use the letter B, stands for that point. Again, has become kind of a standard. So to be consistent with that, we are going also to use the same letter B for that, and now we can come up with equation of a line in another way. So let me see, I have that one, yes I do, and let me put it up for you. Again, hopefully they are large enough so that you can see that, but you have an upper hand to your computer, you can always zoom it, and then you can make it larger so that if you like to take any notes. But here, my point that I selected, instead of saying 0, y1, the point on the line, I called it 0, comma b, and here it is y minus y1 over x minus 0, because the coordinate of that is 0, is equal to the slope of the line. And then I come back, instead of y1, I use the letter b, and I said y minus b over x minus 0 equals to m, and very elementary algebraic manipulation, cross product, I came up with this formula. And this formula is a analytical equation of a line, or any line except vertical, and B stands for the y-intercept. So again, the advantage of this to the previous one is that in this notation, if we represent line, we are also dealing with function relation. Y will be independent variable, x will be dependent variable. Now, going back to the vertical line I mentioned, vertical line, as you know, I don't have to draw anything. We have y2 minus y1. We can have the length of y2 minus y1 for any two distinct points. But when you hit the x-axis, then x1 minus x2 or x2 minus x1 will be same point. That means y minus y1 or y2 minus y1 over x minus x, they're same x, that means denominator will be 0. And if the denominator of a fraction is 0, some people they call it infinity, but I rather not to. The best is to call it undefined. So we can say that a slope of a vertical line is not defined, meaning we cannot put any kind of numerical value for that. Okay, now I hope that this lecture was beneficial to you. And the other thing that we notice, I mentioned, is the angle that the line makes with the horizontal axis, and that brings the subject of trigonometry into the picture, and that will give us another kind of analytical representation of line that we can have possibly much more benefit from that. And that is going to be for the next lecture. So I wish you all prosperity and happiness and good health, and please stay safe, and I hope that this, I'm repeating myself, this lecture was beneficial to you. Until next coming video lecture about line making angle with the x-axis, I wish you all good health. So please stay safe. So long.